Let's take a look at the blood pressure lab and what you were supposed to do, and also answer the questions at the end. First thing I would like to address is table 11.1. That needs to be changed because the guidelines have changed, and hopefully you got a chance to listen to that Mayo Clinic, the report there. It was 2 short video clips that I posted for you on Canvas, and they're explaining the new guidelines. I put them here in this chart for you. Normal blood pressure is defined as systolic less than 120 and diastolic less than 80. And elevated blood pressure is now defined as 120 to 129, and on the diastolic side, still less than 80. So that's already elevated. That used to be pretty much normal. Nobody would do anything. And stage 1 hypertension is from 130 to 139. On the diastolic side, from between 80 and 89. Stage 2 hypertension, if your systolic pressure is more than or equal to 140, and your diastolic pressure is more than or equal to 90. And the hypertensive crisis is if your systolic pressure is above 180, your diastolic pressure is above 120. So please change these numbers. You have the old guidelines in there, the new guidelines. Take into account that how much wear and tear high blood pressure does to your cardiovascular system, and how much it increases the risk for very serious complications such as heart attacks and strokes and things like that. So scrolling through the next few pages here, you should know this formula right here that we already had in the heart lecture. Flow is proportional to the pressure change over the divided by the resistance. And here are the 2 calculations of the mean arterial pressure. You can either take the pulse pressure divided by 3, that's this formula right here, plus the diastolic pressure, or you can use this formula right here where you're taking the systolic pressure plus 2 times the diastolic pressure divided by 3, and we had that on the front page. And then here I already showed you, this is the setup, the normal setup with the sphygmomanometer, the cuff, and then your stethoscope that will listen to the sounds of cord cough. And here we already took a look at this diagram here also. That shows you the first sound of cord cough is equal to your systolic pressure, and the last sound of cord cough will be a diastolic pressure. And here are 2 more important formulas. The cardiac output is equal to the heart rate times the stroke volume. That was also in the front. And here's some more explanations that you can read through. The stroke volume is equal to the end diastolic volume. It means the maximum filling of your heart at the end of diastole. And then subtracting from that will be the end systolic volume, which is the volume of blood that's still left in your ventricle after the heart has contracted. A typical stroke volume is about 70 milliliters. And scrolling through more stuff here, the heart sounds. We said we were just going to focus on the vowel closures. So heart sound number 1 and heart sound number 2, the typical lub-dub of the closure of the vowels. So you have 2 sets of vowels. The AV vowels are right here. This would be right here, the first one, and then you are on the left side, the AV vowel right there. So they are also called tricuspid vowel here on the right side, and bicuspid vowel on the left side. Also sometimes called mitral vowel. So it has 3 names of all things for the same thing. Either way, so the AV vowels, when they close, you hear the lub sound in your stethoscope, and when the semilunar valves close, they would be right here. So here would be this one here is the pulmonary semilunar valve, and then barely visible right here, this would be the aortic semilunar valve. These 2 valves, when they close, these semilunar valves, note how they're closer to the surface. You hear it kind of louder, the dub sound, although these valves are not as big as the AV valves. But here you can, if you have a stethoscope somewhere available, you should listen to your heart sounds in different positions where you can hear them loudest. Of course, if you put your stethoscope directly over the valves that you want to listen to, then you hear those louder. but you can read through all of this. Here is a diagram that sort of superimposes the pressure relationship here in the heart. As the heart starts contracting, it builds up pressure. So this would be the mechanical events right here. They're always followed by the electrical events. So here, down here, you have the QRS here. QRS would have to happen first. And then once the heart has been depolarized, the myocardium, then you can build up pressure. So you'll be right here. The T wave, which represents the repolarization of the ventricles, that one actually coincides on a mechanical basis directly here with maximum pressure in the ventricle. But again, the electrical events, as seen on the EKG tracing, they always are ahead of the mechanical events here, in this case the pressure buildup. Now let's take a look at the heart sounds. The closure of the AV valves, you want to close them as you're building up pressure because you don't want any backflow into the atria. So the AV valves, they would have to close right here when you're starting to build up pressure. Now, the closure of the semilunar valve would have to happen as the pressure comes down. So here you have the semilunar valves closing, and that's happening to prevent backflow back into the ventricles. And of course, so they need to close as the pressure goes down so that blood doesn't get sucked back into the ventricles. Next up here on the instructions for the procedures, we have two different versions of how we run this lab normally. Either the manual version, so if you do the manual blood pressure measurement, that's what they do in hospitals a lot of times, and in your doctor's office, it's just a manual blood pressure measurement. It works always. It's fairly easy to do, and it's sort of the standard procedure. And I would have done it in the lab with the manual version of the blood pressure measurement. We can also do it with our setups, and that usually doesn't work with the extra setup. It's also very complicated and simply not worth it. So I'm going to skip over that experiment, the extra setup kind of version. I'm skipping down here now to the data report pages, and so I put some fake data into in this data table right here, something that's reasonable. So you would have had some fun with this lab if you would have been able to do it. Maybe if you have a cuff and a stethoscope at home for some whatever reason, you can try this. Also, they used to have sometimes at CVS Pharmacy, they let you measure blood pressure, but it may not be open right now. So anyway, here's some fake data. Your highest number should be standing. So I put 120/80, which is reasonable, and a heart rate of 70 beats per minute. So all of that is normal textbook kind of blood pressure and heart rate. When you're seated, it may be a slightly lower, but very similar kind of values. So it'll be seated. And then laying down, your blood pressure and your heart rate should go down because you really don't need so much pressure anymore. So here's some data for lying down. And the cold pressure, that's what we do in a lab when we're trying to get the diving reflex going. And sometimes I have a volunteer that's willing to put their head into a bucket of water, ice water that is, we have in the lab. And then you can get that diving reflex going. It works pretty well, actually. You might want to try it at home if you have nothing else to do. Just put your head in a bucket with cold water and see if you can get the diving reflex. Watch the video first that I posted in your Canvas website of how other people have done it. And then if you somehow are able to measure your pulse rate along with it, that would be cool to try that out and see if you can get the diving reflex. But please watch the video first before you attempt this. And then you see how other people were doing it and what they got out of it. There are 2 videos actually posted. So let's calculate the pulse pressure for each one of these. Pulse pressure is simply the difference between systolic and diastolic pressure. So let's fill in the data right here. So here is the data. Be sure that you know how to calculate the pulse pressure. So simply systolic minus diastolic pressure. You get these numbers right here with the given data. And then the mean arterial pressure, you can use either this formula or the other one. It's up to you. Right here, I just put in here, since we calculated the pulse pressure, it's easy to use 1/3 of the pulse pressure plus the diastolic pressure, and then you get the mean arterial pressure. Okay, so now let's answer the questions. How do the systolic and diastolic pressures of the subject in sitting, standing, and reclining positions compare? Well, the highest pressure should be when you're standing. Sitting and standing does not make much of a difference, but when you're reclining or laying down, then it should be slightly lower. The heart rate of the subjects in the different body positions, again, between sitting and standing shouldn't be much of a difference, maybe slightly less in sitting, and then reclining, your heart rate should go down. How do the systolic and diastolic pressures and heart rates immediately after cold pressure compare to those recorded while you're sitting? So with the cold pressure, if you are able to get that diving reflex, then you have a real drop in heart rate and in blood pressure. Now, if you have the ability to measure that at home, everybody can measure heart rate. So all you have to do is to measure your pulse, either the carotid pulse or on your wrist. So that you can do easily, but the blood pressure, you would have to have one of those devices. If you have one, you should try it out, see if you can get the diving reflex, because that's a significant drop. I think the guy that's doing that on that YouTube video, he went down from a normal heart rate of 70 beats per minute to the high 30s, like 38, 39, something like that. Which factor, stroke volume or heart rate, has the greatest impact on the cardiac output? Well, the stroke volume is just not that much wiggle room that you have. You can't really double your stroke volume that well, but you can double your heart rate fairly easily. So remember the formula. Here's your formula. And of course, heart rate and stroke volume are equally important for the cardiac output calculation. It's just a little bit easier to double your heart rate. But also when you're exercising, your stroke volume, of course, goes up too, by a lot. And the contractility increases, your venous return increases, all of that affects the stroke volume, and then you increase your heart rate. You can get up to a cardiac output of about 20 liters per minute. That's achievable. Now, use an equation that relates flow, pressure, and resistance to define mean arterial pressure. So for number 5, here's your formula. The flow is equal to the change in pressure over the resistance. Moving on to 6. The first and the last sound of chord cough. First one, of course, that is used to approximate your systolic pressure. Last sound of chord cough is used to estimate your diastolic pressure. Why is mean arterial pressure not equal to systolic plus diastolic pressure divided by 2? The reason for that is that we're spending more time on the diastolic side as opposed to the systolic side. So we need to double this diastolic pressure plus 1 time the systolic pressure and then divide by 3 to account for that, to get the mean arterial pressure. Define pulse pressure. The pulse pressure is equal to systolic pressure minus the diastolic pressure. So that's there you have to have the minus, actually, systolic minus diastolic pressure. Now for the next question, you're supposed to put the statement in your own words. I'm going to try that. Systolic blood pressure is dependent on the force and velocity of ventricular contraction. So the amount of pressure that you're able to generate, the max force, of course, it depends on how fast, velocity, and how strong the heart would be able to contract. And then the diastolic pressure will depend on the degree of vasodilation / constriction during ventricular relaxation. So how well you are able, your heart is able to relax, that plus the resistance that's still in your cardiovascular system, meaning the how the vessel diameter plays out, all of that determines the diastolic pressure. So moving on to 10, systemic hypertension may be demonstrated by an abnormally high systolic reading, a high diastolic reading, or both. And what underlying problems might lead to a high diastolic reading with a normal systolic reading? A high diastolic reading is when your heart is unable to relax. So basically you have a lot of afterload. You may have too much blood coming back. Your heart is weak. It's unable to process all the blood that's coming back. The contractile force is usually not there, and then you have backup. And so a lot of times this is called congestive heart failure. That is a condition where you would see a high diastolic reading. So a lot of times when somebody has a high diastolic reading, they also have typically a high systolic reading. Now, it could be that somebody has a high systolic reading, but a diastolic reading is not that high. For example, when you're exercising, your systolic reading goes quite high, but the diastolic reading really should not be that high.